Hello, my fellow causal champions. My name is Dan Harris, and I'm your host today on Causal Discoveries. This episode is the series premiere investigating a new, hot-off-the-shelf scientific theory. Oh yes, very exciting. And this theory is called the theory of universal specificity, which directly challenges the venerated theory of relativity. So we kick this series off by asking the question, what if relativity, which makes such shockingly accurate predictions, is wrong in why those predictions are true? Is it even possible for a scientific theory to be a spectacular success prediction-wise, like relativity clearly is, and yet be an utter failure in its explanations for those predictions? We investigate these questions today, and I hope you enjoy this episode on Causal Discoveries. It might surprise you to learn this wouldn't be the first time that this has happened, where a successfully predictive theory is completely wrong in its explanation for its predictions. The geocentric planetary model, where the Earth is stationary at the center of the universe, is probably the most well-known example of a theory making accurate predictions, yet completely failing in its explanations. Over 400 years ago, before Kepler discovered his three laws of planetary motion, Kepler perfected Ptolemy's geocentric model, where the Earth is the center, and it made just as good as predictions as the heliocentric model did at the time. In fact, both models predicted what you would observe in the night sky with equal precision. So I think there's a historical lesson to be learned here, which can be applied to our current inquiry into the validity of relativity. So to help us better understand this historical example, let us welcome our next guest, Johannes Kepler. Thank you. Johann. Can I call you Johann?
Yeah.
I would like for you to please briefly describe the differences and similarities between the heliocentric and the geocentric models, and that were available to you at the time when you were looking into which one was correct.
Yeah, there's no problem at all. Let's see. Where to begin? So they gave me these markers so I can draw on the board in front of me, which you can't see apparently. Very interesting technology. But here's some difference between the models graphically. Okay, so the heliocentric model, the model where the sun is at the center, we're gonna indicate with an H for heliocentric, and we're gonna draw that over here. And then the geocentric, we're gonna draw over there. Okay, with the G, where the Earth is at the center. So for the sun at the center model, we're gonna have this nice yellow fiery ball, which we know is fire now, but I didn't know at the time. And okay, and then around that, we're going to draw the planetary motion. Now, we're trying to draw what the planets are doing relative to the different models, okay? So Earth is going to be important in both, just to understand their relationship. But right now, we're just going to focus on the planets, okay? So you've got this planet here, okay? And we want to make sure we remember that this is the sun, nice yellow ball there. And the planet moves around the sun in a circle. It's not too scale, but it's as best I can do. And the Earth, we're going to use the color green. And Earth, let's say, is that down, all right? And it too revolves around the sun, roughly the same direction as these planets. And so we're going to draw arrows this way. And what's going to be important later is this relationship from the planet to the Earth and its angle space from the Earth. Okay, yeah. So when we get to the geocentric model, the Earth is at the center. Okay, Earth is at the center. There's our beautiful Earth. Okay, and the planet is going to be moving around the Earth. So we're going to try to draw the same distance in the same angle space. Okay, so like the Earth this way is facing, let's say, X and Y, right?
Yeah.
We only have two dimensions here. Z may be coming out of the board, and you also have the X and the Y relative to, let's say, Greenwich Mean Time or something simple like Grand Meridian line, excuse me. And then this distance here, it's going to be the same distance in the same angle space. So we're just trying, the different models do make the same predictions this way, but they just explain the motions differently. So this planet, surprisingly enough, is going to be orbiting around a point in space very, very slowly. An empty point that there's nothing there, okay? So very important to understand. All right, so this is our planet, and that's a void, an empty space. I put an X there, there's nothing there. It's silly, but that's what it was doing for this model, okay? And this point was orbiting around Earth very, very quickly. Now, if the Earth was rotating one way, this would be going the other way, but here we go. So this goes around the Earth very, very quickly. And I have it here going to the point, but it doesn't have to go to the point. This goes around, and then this goes there. The center moving around the Earth. Now, of course, when looking at these models, one looks silly today. That's because most of your high school graduates today know that the sun causes its gravity causes the planetary motions. There's this invisible force here drawing it in, making it circular, see? And they, today high school students know this, but and it makes one easy and seem obvious, right? That this one correctly explains why we observe the planetary motion we do in the sky, okay? But you need to imagine it this way. At the time when I was working out this problem, the solution was not obvious at all. Both theories made equal predictions, equal predictions from what you would see in the night sky. But each of these theories were based on two contrary assumptions that lacked validation. So the assumption for this heliocentric model was that the sun was at the center, and the assumption for this geocentric model was that the Earth was at the center, right? And validating either assumption was out of the question until I came along and discovered which model was correct, yes. And as I entered the debate, actually, the Earth center model won popular opinion at the time, massively popular. Because it felt more intuitive than the other model. But you should always be suspicious of conclusions reached by feelings over reason, in my opinion.
Why was it more intuitive at the time?
Yes, well, the sun-centered, why one was more intuitive than the other at the time? So the sun-centered model required the Earth to rotate 360 degrees all the way around every 24 hours, right? Yes, that's how you get your day and night, yes. Okay, not the sun rotating around you every 24 hours, right? So this meant that the surface of the Earth traveled at what seemed like ridiculously high speeds. I mean, we're talking very high. So you have to understand that we've lacked this concept you guys have called friction in air, right? Air friction, which is, so it seemed ridiculous to postulate that the surface of the Earth was traveling at approximately 2,000 miles per hour. And when on a nice day outside, wind maybe blow only 5 miles an hour. So why the discrepancy? Because this model is intuitively wrong, right? So, of course, air friction explains all this, but we didn't have a concept of air friction. No compute, right? So, yeah.
Johan, I'm dying to know how you validated one assumption over the other.
Yes, my moment of epiphany, yes, I remember it very well. It began when I noticed in the geocentric model that I perfected, by the way. No one else had access to this model before me, see, so I made it better. That's a key parameter within this model. in this model, for every heavenly body, shared the exact same value as all the others. The exact same. And thank you, by the way, to the University of Texas for documenting this historical moment of mine. Yes, the links are below if you want to check it out. Yes.
What was this key parameter shared by all?
Oh yes, the key parameter. That was the all the epicycles of the interior planets. Remember, the motion around nothing.
Yeah.
For the planets that are inside on this model, they're epicycles. And then for the planets that are outside of the Earth, further away, those deferents, this motion of this empty point around the Earth is called the deferent. That value, and including the sun's apparent motion around the Earth, they all shared the same eccentricity value, the exact same one. It blew my mind at how crazy this was.
Wow.
Yeah,
Really?
yeah, this is crazy.
What does this all mean?
Yeah, what does it all mean? Well, this anomaly can only be explained by a common motion, right? Why else would independent moving bodies share the same common parameter? It makes no sense at all. Only one object's motions has had this very eccentricity value in the other heliocentric model. So they all shared it in this one, but there was only one object in this one that had that eccentricity value. Can you guess which one?
I kind of feel put on the spot
It's
here.
okay.
Johan.
It's okay. Yeah, I got you.
You gotta
I
bail
got
me
you.
out.
Yeah, if that's Earth. Earth had the same exact eccentricity value for its motion around the sun. Earth's motion was the difference that made the difference. You see?
I see. Wow. I do see.
Well, that settled the debate for me. The heliocentric model had to be correct. I later proved the sun to planet relationship in mathematical terms. Very simple mathematics. 3 simple laws of planetary motion. And it was Newton after me that they covered the laws that govern the force causing the motion. But without me, there's a very good chance that high school graduates today would still be taught the geocentric model as the primary model, right? Yes?
Yeah, you're telling me. Gosh. Wow. On behalf of all high school graduates, I want to say thank you for your contribution to causal discovery.
You're the most welcome. You're most welcome. And don't forget also that knowing the reason for why the heliocentric model was correct explains why the geocentric model was so successful at making its predictions, but nonetheless very wrong in terms of why those predictions came to be.
How is that?
How is that? Well, it turns out that the geocentric model is the transformation of coordinates from the heliocentric model to the Earth-fixed coordinate system. The model of the motion of heavenly bodies relative to the Earth do in fact move as described by the geocentric model. In other words, motions modeled by the geocentric models are corollaries to the primary causal motions modeled by the heliocentric models. A coordinate change from a causal to a non-causal system.
Wow. I do see why they had to make the same exact predictions.
Yeah, it becomes obvious at this point. Yes, this is ridiculous now, and this is true, right? Yes.
Okay, Johan.
Yes?
So let me get this straight. All right. The first thing to realize, I suppose, is that there was this adopted model, M, which was based off an assumption, we'll call it A, that the Earth was at the center
of course.
of planetary motion. Right. Okay.
Yeah.
But additionally, there existed an alternate assumption.
Yes.
That could just as easily been true, like the sun being at the center.
Yes.
Which meant that
See?
the point 2, there was this alternate model, the
Yes,
heliocentric
yes,
model,
of
where the
course,
sun's at
yes.
the center, based on this
Yeah.
other assumption.
Yeah.
Okay. So the thing that you did to figure out which one was correct, because they both predicted equal things, was you did some analysis on the original model, and that led to an anomaly, a detection of an anomaly. So it implied a detection of an anomaly. We'll call this the exclamation point here, the anomaly, which then can only be explained if our alternate model was correct, and it basically its base assumption was correct. All right, and then with this newfound conviction, the fourth thing to understand is that, unlike Ptolemy's model, which kind of just stagnated for 1,000 years, you managed within your lifespan of discovering this, coming up with causal discoveries, 3 very important laws of causal discoveries that led to causal discoveries. All right, and then this whole thing then led to an explanation for why this model, based on this assumption, is wrong.
Yes.
Right? It was the transformations to an Earth fixed coordinate system.
Yes.
From the real coordinate system. Okay. All right. I think I got it.
Essentially that's correct.
It's amazing. Thank you, Johann, for being our guest speaker today. And thank you again for your contributions to causal discovery.
Bien Ernst. Don't mention it, my friend. Yes, don't mention it.
Wow, what an epic history of causal discovery that was. But how does that help us here with our current inquiry into the validity of relativity? Well, it might surprise you further to learn the following 5 parallels between that history and relativity. Firstly, relativity is based on an unvalidated assumption, which has a compelling and contrary competitor assumption, and that exactly parallels our first point from before when talking with Kepler. Secondly, relativity has a partially completed competitor theory based on this contrary assumption, and that partially parallels our second point from before when talking with Kepler. So we'll put little dashes in there. Now, it actually will become completed later when we get to the other parallels. But for now, that's the information we have, so that's where we're at. That partially completed theory is called the Lorentz ether theory, and it makes the same exact verifiable predictions, the same exact, as the special theory of relativity. Now, the reason it's only partially completed, or at least why I'm saying that, is because the Lorentz ether theory does not extend into a theory of gravity like general relativity does. It doesn't have a model based on an assumption for gravity. But that doesn't mean a gravitational theory consistent with the Lorentz ether theory cannot exist, as we'll see shortly. So most honest, well-educated physicists are aware of these first 2 parallels, which should be sufficient, given our history, for the scientific community to further inquire into the validity of relativity, or at least downgrade its status to a working hypothesis, so long as these 2 assumptions, these 2 competing contrary assumptions, are equally plausible. So the parallels don't stop there. Recall we had 5, so let's continue to the third one. The third parallel was, when analyzing relativity, it has led to an anomaly that can only be explained if relativity's contrary assumption were true. And that exactly parallels the third point here from before when talking with Kepler. Now, the fourth parallel is where we start to complete the second one, so we'll get back to it right now. Now, I developed a new theory based on a slight correction to the Lorentz ether theory, which does extend into gravity, and it competes with relativity. So that completes the second one. Now, this theory would have completed the Lorentz ether theory if it weren't its own theory based on a slight correction. So, to the fourth parallel, as I was developing this new theory, I too made many fascinating causal discoveries, just like Kepler did as he progressed the heliocentric model to its fully developed elliptical form, where the circles from the heliocentric model turned into ellipses, which are oval-shaped. And the many causal discoveries I made exactly parallels our fourth point here from before when talking with Kepler. This new theory I discovered is called the theory of universal specificity. And there's a reason for the term specificity. It's not just a jab at relativity. So moving on to our fifth point, or fifth parallel, the theory of universal specificity explains why relativity is an excellent predictor, but nonetheless wrong. It basically boils down to a transformation to either an object fixed reference frame or some other reference frame from the universal reference frame. Just like the geocentric model is a transformation to an Earth fixed reference frame from the correct solar or sun's reference frame. And that exactly parallels our fifth point here from before when talking with Kepler. And all of these parallels will be covered in more detail in further episodes in this series. So as I wrap up this episode, I wanted to remind you that this video series is dedicated to presenting the theory of universal specificity and the causal discoveries made during its development. To see the status of the series production, please reference the WordPress link below, which captures the draft outline of this video series and the progress of its development. And do please hit that like button if you enjoyed this episode, and leave a comment or question below. Lastly, don't forget to subscribe and stay tuned to this channel as we continue to develop, produce, and release new content on causal discoveries.
Let's go. Yo, I'm like an addict, do I gotta have it. I ain't even playing, got a really bad habit. If it moves, gotta grab it, fuse like a magnet. Lose, won't have it till I'm doomed in a casket. I ain't playing, got a weird mind. If you work 8 hours, I'ma work 9. If the shit tastes sour, you should taste mine. I'ma stay in power for a long time. Get up, nah, I ain't a quitter. Toss me the ball, I'm a really big hitter. Big picture, I'm a straight killer. Rising the song to the highest bidder. Got juice, got gas, I'ma move fast. New shoes, new tracks, like who's that? I'm new, come back, better than last. Yeah, it's a new me, never gonna look back. I'm never gonna look back. Cause damn, I was built to last. You move slow